In this video, we're going to think about the generalization of a system of equations into those three representations. So if I have this system over here, we've already expressed that as a vector equation and as a system of linear equations. The immediate extension that we could make here is that we already know when we're using Gaussian elimination that we're going to enter these coefficients into a matrix, and that we're going to have this as our final column in that matrix. So this representation would be 1, 3, 5, and 2, 1, 5, like so. And of course you could put the dotted line down the center to indicate where that equal sign is. That's not ultimately necessary. But notice that what we've done here really is that this vector has taken the place of the first column, and the second vector has taken the place of the second column, and then the vector that we're trying to get to by taking a linear combination of these two vectors. Remember, so what we're trying to do is take 1, 2, we're trying to take the 1, 2 vector, and then the 3, 1 vector to get us to the point 5, 5. Or we could write that as 5, 5. The vector 5, 5, remember, is the vector that extends from the origin to that final tip. So we want to know what multiple of the 1, 2 vector. If this represents the 1, 2 vector, some multiple of that, in fact, m multiples of that 1, 2 vector, plus h multiples of the 3, 1 vector should get us to the point 5, 5. So if you think about these two vectors as basically as being the columns of the matrix, because they really represent the coefficients of m and h, and you think about the constants as basically being the third vector inside of that augmented matrix. Remember, this is called an augmented matrix. Augmented means it's enlarged, augmented by the constants that are in that equation. That's where we're augmenting the matrix. Okay, so this is some terminology that we need and is going to become very, very important. If the above system has a solution, then we say that 5, 5 is a linear combination of 1, 2, and 3, 1. Well, what does it mean to say linear combination? Well, whenever you combine something linearly, you multiply and add. Okay, so notice that we're multiplying 1, 2 by m, we're multiplying 3, 1 by h, and we're adding them together. So a linear combination is basically a way of saying scale, sum. Scale and sum. And what you're visualizing when you think about linear combinations is you're thinking about this picture right over here. This is what linear combination means. It means, can I scale the first vector by something, add some scalar multiple of the second vector to it, such that I arrive at my destination, the desired point that I would want to arrive at, which in this case is the point 5, 5. So in this case, yes, because we know we can take the 1, 2, and 3, 1 vectors anywhere in 2 dimensions, 5, 5 is definitely going to be a linear combination. We would have to reduce this system, which we can now do with our technology, and then that would give us the exact values of m and h that we would need, the number of hours that we would need to ride the magic carpet and the hoverboard to make it to the destination 5, 5. An equivalent way of saying this is 5, 5 is in the span of 1, 2, and 3, 1. Or you could write it like this. You could say, yes, 5, 5 is in the span, bracket, and then the list of vectors that it's in. What we mean by span is if you think about it as a wingspan, if you think about that's how far that those vectors can sort of stretch out, right? So in the context of these two, these allow me to span all of R2. So I could say that the span of the vectors 1, 2, and 3, 1 is all of R2. And in translation, what this really means is that we can get to anywhere, get to any point in 2 dimensions. And the reason we can do that is because of this idea of this slanted grid system that Basically, I could take any fractional component of that I want, and then I can move off that trajectory by taking the 3, 1 vector. We'll explore this in another video a little bit more, but for now, there are just two ways of saying that this system has a solution. That phi 5 is a linear combination of those two vectors, and that another equivalent way of saying this is that phi 5 is in the span of those two vectors. And this is the notation that we use to denote that. So in general, let's think about the general system that we have. Okay, so in general, this is kind of where everything comes together. We can say that if we have a system that looks like this, A11 X, what do we want to call this? Let's say A1 X11. Better yet, our coefficient we'll call A11. So that means that that's the coefficient for the first row, first column, times the first variable, plus first row, second column coefficient, times x2. And this is going to go on. We could have as many of these as we would like. So we're going to say in this case that we have A1N xn. So basically we're saying we have n variables. And that's going to equal some constant. And so then we're going to have the second row, A21 x1. So some new constant times the first variable, plus some new constant times the second variable, all the way down to A2n times the nth variable, equals some constant C2. So our coefficients are the only things that are changing from row to row, as well as the constants on the end. Well, I don't know how many of these I'm going to have, right? So I could have just as many equations as I do variables. I'm not going to assume that, because that doesn't always happen. So to make this general, we want to make the most concrete possible statement we can make. So we're going to say that we have m rows, AM1. So this is the mth row times the coefficient there times the first variable, plus AM2 times the second variable, and then I don't know how many variables I'm going to have. I know I'm going to have n of them, so this is going to be the mth row, nth column, and times the nth variable equals some c sub n. So we don't know how many rows there are in there. All I can say for sure is that here I'm going to have m equations, and I'm going to have n variables, or n columns. Okay, with that said, we can put this together as follows. We can say that, well, really the only thing that changes in this first column is, you can see the x1 is in all of those in that first column. So this, what it looks like is this is going to be x1 times the vector containing a11, a21, all the way down to am1. So this is just different rows, first column, plus x2. We can see that that's consistent across here. So if I factor out an x2 and write it as a vector, I'll have a12, a22, all the way down to the mth row, the second column. And then, of course, I'm going to have all of this in between here, plus dot, 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 plus. And then here is going to be xn, because I see that that's consistent among all of these equations, times a1n, so there's a1n, a2n, all the way down to amn. And that's going to equal all of my constants, so C1, C2, all the way down to Cn. So what we have here is an m by n system. We have m equations, n variables. Is it possible that m equals n? Absolutely. In some contexts, you have just as many equations as you do variables. But the way we're writing this is to make it general, meaning that this is going to apply to every situation. Any situation that we can encounter can be represented by this generalization. Now, let's give these guys labels. Let's call this vector. This is a vector, so I'm going to call this A1. And the reason I'm going to call it A1 is it's the first column, and it's a column vector. And this is going to be A2. This is going to be AN. That's the nth vector. And this is going to, I'm just going to go ahead and call this the vector of constants. You know what? We can call it C. I'm going to call it B. I know I called the components C1 through Cn, but I'm going to call it B, and that's just to be consistent with something we do later on. So as a augmented matrix, the way we can write this is, of course, we just list all the coefficients of x1, x2, all the way up to xn. But to avoid having to write a lot, really it's just this vector is going to go into the first column of my matrix. So I'm going to write in A1. Right there, that entire column, which is going to span up and down, is just going to be the components inside that A1 vector. The second column is going to be A2. And there's going to be a bunch of these columns in here, or n of them anyway. And then we'll have AN here. Our equal sign would be there, and then over here we would just have that B vector. So this is a really powerful way to represent something. We've just said that the coefficients are vectors themselves. The constant is a vector. The constant vector is a vector, and so our system of equations is really this exact same thing here. Which once again, if we did want to extrapolate on this, we could say, well, this is really just A11, A21 down to AM1. The second column is A12, A22, all the way down to AM2, ... This would be let's see, yeah, 1n, A2n, all the way down to AMN. And then our constants here would be C1, C2, all the way up to Cn. So these are equivalent. These are the same thing. They're just, one's a little bit more compact in that we just say it just has a bunch of vectors in it. So that's really what we want to get at here. In the next video, we'll elaborate a little bit more on linear combination and span. And if the span isn't all of R2, how do we determine what it is?